Hey, welcome to Ones and Zeros. My name's Ben, and today we're going to be taking a look at using rotary encoders with the STM32 devices, specifically using the timer peripherals in the STM32 devices to allow us to leverage the hardware in order to be able to decode the particular signal from the rotary encoders. So whereas you've got a standard sort of potentiometer that will give you an analog signal that you can use an analog to digital converter with, a typical rotary encoder like the ones we've got here, so like this one as well, see if we can get that to focus on that one. So these guys actually put out what is known as a quadrature signal, and that is basically two digital lines that put out a signal, which we're going to take a bit of a look at so you can see how that works. And we use the timer peripheral on the STM32 to actually decode that for us in hardware. You can sort of set up a bit of a bit banging system to be able to do that just using standard GPIOs, but that does use a bit of extra CPU, and it's really cool to be able to use the timer peripherals to do that without having to use that extra CPU and get a bit of a hand in making that work. So what we're going to do in today's video, first up, is we're going to have a bit of a look at what the signal looks like using the oscilloscope that you saw we had set up there. So you can see sort of how that works. Then we're going to go through and have a look at what it takes to actually get one of the timers set up with the rotary encoder. And then following that, we're going to go through and have a look at actually getting a driver written so we can actually use it a little bit more dynamically like we've done in some of our previous videos. So it's kind of plan of attack for this video. Also, big thank you to the new subscribers and followers on Twitch and YouTube. It's really cool to see people seem to be enjoying the content that I'm putting out, so really happy about that. Um, and there will also be a few more videos coming over the next few days as well. So there's quite a lot that I've got planned. It's just a matter of actually getting the time to get them done. So let's get stuck into it. We'll have a bit of a look at these signals. So basically got the same STM32F411 Nucleo 64 board that we've been using for our external interrupt and timer videos that we've done. That one's got this rotary encoder here hooked up to it. So just taking power, ground, which is the orange wire here, and the yellow wire is connected to 3.3 volts. And then we've got our blue and our green wires, which are the two digital signals coming from the rotary encoder. There's also the purple wire there, which is hooked up to the push button. So the rotary encoders do actually have a push button that you can use, but we're not don't have that one hooked up at the moment. That one just works through sort of a standard GPIO like we've looked at in previous videos, or you can hook that up with an external interrupt and use it that way as well. So a couple of options there. But we're just going to be looking at the rotary encoder part in this video. We've also got another rotary encoder, so this guy here, which is just hooked up to power on the Nucleo board. And then we've got the two signal wires coming from that, which are connected to the two channels that we've got currently displaying on the oscilloscope. So if we have a look at sort of the pinout of this guy, get that to focus there. So bottom to top, we can see we've got our ground or minus, our positive, which we're just using 3.3 volts for the Nucleo devices. And then that focuses a bit better for us. Then one in the middle is marked SW, so that's the push button. And then we've got DT and CLK, which are the two signals there. So it's kind of labeled as data and clock, even though I kind of see them more as just two complementary data signals rather than a data signal and a clock signal. But we'll have a look at sort of what sort of signal we get from those first up. So let's pop the triggering for the oscilloscope in the mode we need there. And if we turn the encoder just one notch clockwise, we can see that we get a bit of a signal on both of those digital lines. So we can see with that one, the top signal here has gone from 3.3 volts down to 0. And then following that, the next thing that happens is that the second line goes down to 0 as well. Then the first line comes back up, followed by the second line coming back up. So that's kind of a rough look at the way the signal works there, in that case when we turn it clockwise. So if we turn it anti-clockwise, like that, we can see that it does something similar, except the difference is that the two lines happen in opposite order. So our second line is the one that goes to 0 first, followed by our first line, then the second line comes back up, and the first line comes back up. So that is what's known as the quadrature signal. So clockwise and anti-clockwise. So that's kind of the signal that the timer is going to be decoding for us. And let's jump into some code and see what we can make happen with that. So just using the code as it was from the end of the last stream, so when we were doing the timer interrupts, and there was actually a bug I noticed with this one, with the code that was I put up onto GitHub. So it was some of the folders weren't set up quite right for when it's in our release configuration. So we go to our build configurations. So it was set up in release configuration. I hadn't actually got the source folder set up properly for that. So if you were having troubles getting that to build, that was probably why. But that's now fixed and compiles as it should in both debug and release at the moment as well. If anyone does download the code from GitHub and spots any bugs, feel free to let me know about it, because if I haven't spotted them, I'd much prefer to go in and get them fixed up so that other people can use the code a bit easier as well. So let's first have a look at sort of what it takes just to get the timer set up to decode the quadrature signal from the encoder. And once we've done that, as I mentioned, we'll go through and actually write a driver. So just in our initialization part here in our main.cpp, prior to our processing loop, and just after where we set up the timer from last time, I've just disabled that timer we were playing with last time, as well as our external interrupt. So we're still setting those guys up, but not actually enabling them. So just pop a comment in there so that we know what we're doing. And let's get some code sorted out for that one. So a couple of things that we need to set up first up. We need to set up the 2 GPIO pins that we're using for the quadrature signal. Then we need to go through and get the timer peripheral set up, and then it's just a matter of capturing data from the timer's counter register. So essentially the way it works is that the timers, the actual counter within the timer is being triggered by the quadrature signal directly rather than from a clock, like the way we did it when we did the timer last time. So we were using the prescaler and things like that to determine the clock rate of the timer. In this instance, it's actually the quadrature signal directly, and those the edges that we saw on the oscilloscope that are actually triggering the counter to either count up or count down, depending on whether we're turning the encoder one direction or the other. So let's get these GPIOs set up. So we're going to need a GPIO init type def. And we're just going to be using timer 3 on this one. And I've just got the quadrature signals hooked up to pins B4 and B5. So create that one, fill it with zeros. And we'll do both of these pins at the same time. So we want GPIO pin 4 and GPIO pin 5. And I'm going to go with alternate function push-pull mode because we're using it connected to the timer rather than as a standard GPIO. Not going to be using pull up or pull down resistors on that one at all. Our speed we can just set to low. And set our alternate. Which in this case we'll be using alternate function to timer 3 for that one. And we're using GPIO port B for that one. Pass in the init structure, and that's our GPIO setup there. So first thing we're going to need for the timer will be a handle type def. And let's call that encoder handle. Now, there's only a few bits that we've really got to set up in this case, so we've got to tell it which timer we're going to be using. And we also need to set our periods for this one as well. So that should be init period there. That's a bit better. So the period's basically just going to determine at what point the counter wraps around. So if we've got it set up so that the counter is increasing as we turn the rotary encoder clockwise, then it means that once, if we turn it clockwise enough, once it gets to 1024, it's going to wrap around back to 0 at that point. And that's just kind of an arbitrary value that we're throwing in there. Tends to be what I use whenever I'm using rotary encoders for a project. So also set our repetition counter to FF. And it's not actually going to be using the prescaler, so just set that to 0. Because of the fact that the quadrature signal is the thing triggering the clock rather than a clock source within the STM32. And we're not really going to be using counter mode either, because again, that's determined by the quadrature signal, but we'll just set it to up. And we'll throw in our clock division as well, but again, it's more just setting it so that we know that it's been set to a value rather than... Might help if we spell that correctly. Okay. So the other structure that we're going to need to fill out to be able to initialize this is a timer encoder init type def. Just call that enc init. Again, we'll fill that one with zeros. Might help if we can type correctly. Okay. So set our encoder mode, which will be TI12. Been rather a warm day here, and it still would be nice if it cooled down a little more. So we'll set our IC polarity for IC1, and that'll be rising. IC1 selection. which we'll go with IC selection direct TI. Encoder init IC1 prescaler. Should be ICPSC. There we go. And that will just be div1. Capitalize that I, might help. And this will be IC1 filter, which we're just going to set to 0 there. Generally find setting the filter to 0 works perfectly fine. I don't tend to find there's too many issues with noise within the signals there. And we're just going to set the values for IC2 the same as we have for IC1. And that's all we need to fill out in that particular structure. And then we can go through and actually get it initialized. So in this case, we're going to use HAL timer encoder init. Pass it the handle as well as the encoder init structure. Fix that guy out there. And then if that doesn't succeed, then we'll send a message out via serial, turn on our user LED and pop it into an infinite loop. Like so. And if it has succeeded, then I'll pop a message out showing that that has worked. And that's basically all we've got to do for the actual initialization. Now, we're not going to do too much with this just as a bit of a demonstration right now. We'll go into a little bit more depth once we go through and write the driver. But at this point, what I'd like to do is just get it to capture the counter value from the timer maybe once a second and spit that out to the serial just so that you can sort of see what the time is actually giving us to work with as far as an actual value. So we're just going to pop in here string.h and leave it standard IO that we're going to need for that one. Looks correct. So just so that we can use the sprintf function to format what we're going to send out. The other thing that we'll do just up a bit further in our main, just with our heartbeat tick thresholds, is we'll pop in a encoder tick thresholds, and we'll set that to 1000 milliseconds so that we get our 1 second update rate. Go back down to our processing loop. If it wants to scroll correctly. Where are we? There we go. And we're just going to pop in another uint32 there and use that for our encoder update value. Similar to what we've done for our update heartbeat LED. Yes, we'll just increment our encoder ticks value by the number of ticks that have passed since the last loop. And if our encoder ticks value has gone past our encoder tick thresholds, then we know that we need to do something with that. And we'll also subtract the tick threshold value from that to sort of reset it for the next iteration. So that way we get our constant 1 second update from that. So first things first is we'll grab the value from our timer counter. So just going to use how timer get counter. Pass it our handle. And we'll create a string, just a C-style string. And we're going to use sprintf to format that for us. And then we'll send that out via serial. Excellent. Let's see if that wants to build for us. 2 errors. What do we got going on there? Ah, misspelled that one. Wonderful. All right, let's pop that onto our device. Pull up our serial terminal here. And not actually getting anything from that. So possibly something we haven't set up correctly here. Let's just jump back to our serial and let's just do a reset of that one. So it does initialize, and we are seeing that the encoder is showing that it has initialized correctly. Just double check that we've done everything correctly there. GPIOs are all correct. Timer 3. All of our init stuff for our timer base looks good there. However, we haven't actually enabled the timer, which is probably a helpful thing to do in order to get it to function for us. So we want to do how timer encoder start on that one. Pop in our encoder handle and tell it to do all channels for that one. And let's see how we went this time. Still not getting anything when we rotate the encoder, which is a little strange. What have we missed? It would probably help if we enabled the clock for the timer as well. Make sure I type that one in there correctly. Okay, so should be that one. So enable our clock. And I don't believe there's anything else we need to be doing there now. That should behave for us. Always helpful to make sure we're not missing steps. There we go. All right, so for every, let's jump to the screen. So for every single notch that we turn clockwise, we'll see that our encoder value is actually increasing by 4. And the reason for that is because we're actually getting 4 of those edges from the encoder, from the quadrature signal, as we saw on the oscilloscope. So that's why we're seeing it jumping up by 4. If we turn it back the other way, see that it actually decreases by 4 typically as we go each way there. And that gives us our values that we're seeing there. And we can see if we go down all of the way, that it will actually wrap around based on the period value that we provided it in the initialization structure. So if we turn it back clockwise, it'll wrap back around to 0 and go back from there as well. So kind of gives you a bit of an idea of what that actually does to the timer's counter. So when we do the driver, we'll actually be doing a bit of decoding on that in order to determine how many notches the encoder's actually been turned. So we don't really want it to register 4 steps for each click of the encoder. In order for it to be used nice and easily with, say, a user interface or things like that, it's much better if we get it to register sort of 1 click for each of the clicks of the encoder, or -1 for each click if we're turning it anti-clockwise. So we'll take care of all of that in the driver that we're going to write in a moment. So let's get rid of that one. And we're going to make use of the timer manager that we did in a couple of streams ago, in order to be able to dynamically allocate the timer resources and things like that, much as we did with the timer interrupt or the timer basics video that I did recently. And going to be doing it similarly using a class as we've been doing with a bunch of our drivers, so that we can sort of set it up that way. So let's comment out this particular code here. I'll leave that in there for the moment. And I might leave that in there for the bit that goes up onto GitHub this time around as well, just so that if anyone wants to see how that works and actually get their hands on that code and have a bit of a look at that as well. We're going to leave our update in here because we're going to be using that for testing the driver that we write for that one. So first things first, let's get some files popped in here. So header file, and I'm just going to call that encoder.hpp and encoder.cpp for our source file. Copy across our header from one of our previous files. We are going to need our timer manager. I'll just rename this stuff, however. The date today, 28th. Now, next video in our STM32 basic series is also going to be making use of timers as well. So we're going to have a look at how timers can be used for doing pulse width modulation. With the specific example we're going to be looking at being to control the brightness of LEDs, although you can use it for things like driving servo motors and things like that as well. And for that, we'll also make use of the oscilloscope in that one so that we can actually see what the signal is that we're actually getting out of the STM32 in that instance as well. I find if you can actually see the signal, sometimes it makes it much easier. I think as much as there is quite a few different tools that you can use to be able to work with microcontrollers, I think the oscilloscope is a really, really useful one, especially with the particular scope that I have. I think it was one of the only ones I looked at in its price range that does digital decoding, so able to decode like UART, SPI, I2C, CAN, all of those protocols, or without having to spend extra money to get that added to the oscilloscope. And that sort of stuff can be really useful for figuring out if you've got, say, a microcontroller and a peripheral that aren't communicating properly, being able to see what the signals are that are being sent in between them helps to find exactly where the issues are much easier. So rather than get distracted and talking about that too much, let's continue on where we were up to. All right, so we got those files set up and ready to go. And I might just grab a quick bio break and then we'll get in and get this driver written and get it tested and go from there. So be back in a couple of minutes. And we are back. So, beer is refilled, bladder is emptied, and we are good to continue. Alright, so grab the particular bits that I want for this one. So, similar to what we've done previously, we are going to use a initialization structure to be able to set our encoders up. So we're going to get that one sorted out first. And we're just going to call that one encoder init struct. Like so. And okay, indent sorted out there. And we're just going to call our class QAD encoder. Some space down there so that we can scroll a little bit better. Now, particular bits that we're going to want in our initialization structure. So we're going to need to know information about the two GPIOs, and we're also going to need to know which timer we're actually going to be using to set the encoder up. So we need a GPIO type def, grab a pointer to that one. That will be our channel 1 GPIO. And naming them channel 1 and channel 2 because the encoder is actually using the first two channels of the timer in order to do the encoder setup there. And we're going to need to know what the alternate function is as well. The same thing for channel 2. And our timer. Like so. Now with this one, we need to keep track of a few different bits of information in our class. So our first bit will be what our maximum value will be. So this will be the value that actually gets put into the period of the timer setup, similar to what we did before. In this case, we're going to stick with 1024. Also going to want to store our GPIO info, channel 1 GPIO. In and our alternate function. Just copy and paste those guys. Use those for channel 2. And I want to keep track of which timer we're making use of. I want a handle to the timer for accessing the HAL methods for that one. Going to need to know whether we've actually initialized the encoder as well. So similar to what we've done for some of our other drivers. Just going to use the init state enum for that one. And also whether or not it's currently active. So we'll use our active state enum as well. So the ones that we've defined in our setup.hpp previously. So these guys here. Now, to track our data with that one, we'll store what our old and our new values are so that we can figure out what the difference is between those two values. So this will store the previous and current counter values for the timer peripheral. Going to have an int16 there, which will store the difference between those two when we calculate that. Also might track what the acceleration value is as well, so how fast we're actually turning the encoder, which may come in useful when we start to go through and do some user interface stuff using encoders, which we will be doing in our Discovering STM32 series moving forward on that one. And we might also set it up. These guys should be private, so let's move those up there. It's a bit better. Might also set it up so that we can have a couple of different modes with this one as well. So either just a normal mode or an exponential mode. So where normal mode is each notch that we turn on the encoder equals a value of 1 or -1, depending on which direction we're turning it. But we might also have an exponential mode as well, so that if we turn it multiple times, then we'll actually get a larger value, so that if we're trying to scroll through something quicker, it will allow us to do that a little bit easier, but will also give us the ability to just step through one item at a time a little bit more finely as needed. And generally, I find the easiest way to do that is to basically cube the value. So multiply it by itself twice, effectively. Get that right in my head. Which means that if we turn it just one notch, we're just going to get a value of 1 or -1, depending on which direction. But if, say, we turn it twice, then that's going to be 2 multiplied by 2 multiplied by 2. So actually give us a value of 8, which allows us to sort of step through things a lot quicker. And for some of the projects that I've done with using encoders, I find that gives a nice degree of control over whether we want to get through particular settings or things like that really quickly or a little bit more finely. So let's call these encoder mode linear. Set that one to 0 and encoder mode exponential. And we'll keep track of what mode that's currently in as well. Just call that ME mode. And let's get some constructors set up for this. So we're going to delete our default constructor because we are going to want it to require us to provide an init struct for it in order to be able to initialize the class. So grab our default constructor and we're just going to delete that one, and then we'll create one that allows us to pass in our QAD encoder init struct. And let's get our member list set up for this one. So that one, and a 1 pin. Should be U channel 1 pin. Now alternate function. The same for channel 2. That one should be a P. channel 2 pin, channel 2 alternate function. And we need to do our, really can't type at the moment, our timer. Set our handle to all zeros. Set our init state to not initialized. Our active state to inactive. Value old was set to 0, same as value new. And our value. And might make it so that we can pass in our encoder mode in our init structure as well. So let's fix that up. Which does mean that we're going to have to pull that out of the class. So we'll pop that in here. And we'll rename it to Rotary Encoder Mode. Like so. Means we can get rid of that public section there as well. Pop that guy in there. Have to rename that one as a result. And then we can pull our encoder mode from there. And that all looks good. So that's everything. Now, state is not... it's because we gave it a different name up here. Let's just call it ME state. Fixes up that one. And we are going to pop in a destructor for this one as well, so that it can come through and deinitialize stuff when we go to destroy the class, it will actually stop using the timer and the GPIOs and things like that. So if our mode is currently active, it will call the stop function, which we'll define shortly. And if it's initialized, then it will go through and deinitialize that. All right, so that's constructors and destructors done. Let's get some initialization methods in there. So our init method, don't need to pass anything to it because everything's been provided in the init struct already. So that's already sitting in our member variables. However, it will return a QA result just to say whether it's been able to initialize correctly or not. Pop our dinit method in there. I want some control methods for that one. So to be able to start and stop the encoder as needed. So that way, if we want to temporarily disable the encoder, we don't have to completely deinitialize everything. We can just tell it to stop for the moment and then tell it to start when we go to continue. Depending on what we're doing as far as a user interface that's actually connected to, that sort of stuff can come in handy. We're also going to want an update method, which basically will get called to go through and recalculate the values. So it'll pull the current timer counter value, compare it with the previous one, determine whether or not the encoder's been turned, how fast it's accelerating, all of that sort of stuff. So filling out some of the variables that we've popped in there. Now also want to be able to find out whether it's currently active. So pop a getter method in there to do that. Want to be able to get what the current value is and what the current acceleration is as well. So create some methods for that. And then we will also want to be able to set the encoder mode, whether it's linear or exponential, and also retrieve which mode it's currently in as well. So we'll make some methods for that as well. So that'll be QAD encoder mode. And also a mode to retrieve that, a method to retrieve that. And similar to what we've done previously, is we're going to pop another private section in here and initialization methods there as well. This one should be perif init, and we want perif dinit. Now we're going to want to be able to set our dinit mode. So similar to what we've done with the other drivers, we want to be able to either partially or fully deinitialize the driver, so that if it fails partway through initialization, we can just do a partial deinitialization to get it back to where it was prior to starting the initialization, so it can fail gracefully. But if it has completely initialized, then we want to fully deinitialize it, so that way we can have control over which one of those it's actually going to do, which is the same we've done for a fair few of the drivers so far. So keeping things consistent as well, so that if you've seen some of the previous videos that we've done, this will all kind of make sense. All right. And we'll also just create a couple of tool methods just to be able to clear the data, as well as to help us with calculating. Actually, no, we'll just go with one to be able to clear the data. Do the other one in our update method. So let's just call that, that'll be a void clear data. And don't need to pass anything to that. All right, so that's basically all of the methods that we're going to need there. Let's grab those guys and pop those in our CPP file. Go through and start to get these laid out a little bit. I'm just using a similar sort of layout to what we've been doing previously as well. Again, just to keep stuff nice and consistent. Grab that guy. And that one. And just keeping all of these in the same order that they're in the class as well just helps make things a little bit easier when you're jumping between the header file and the source. So for the person that asked in the chat what a rotary encoder is, that is one of these guys right here. So like a potentiometer, but using digital signals. I recommend to jump back to the very start of the stream because I do actually go through and sort of explain a bit more about what they are and how they work, as well as showing on the oscilloscope what sort of signals we get out of them as well. So to give you a bit better understanding on that, that will help there as well. So basically like a continuous dial, similar to what you'd see in some car volume controls, things like that, microwaves, some microwaves and stuff use them as well. And as far as what we're trying to build, basically just going through and showing how different devices can be used with the STM32 microcontrollers. So the final goal with a bunch of the videos and stuff that we're actually doing is to build a bit of an operating system that we can use for multiple different things. And the IDE that I'm using, this is the ST Microelectronics Cube IDE. You can also use things like Visual Studio and stuff like that as well. So those can be set up to be able to work with this as well. And I've tried to keep the code so that it's not super specific to Cube IDE, although it would be easier to set it up and work with that. And the code from this stream is also going up onto GitHub from the end of, usually about 5 minutes after the end of the stream. I'll be popping it up there and putting a link to it in the description as well. So you can also check out some of the other things that we've been working on as well. So every stream that we do add sort of different things to the code. That's all being built up in the GitHub repository for this one. So that way, if someone wants to go through and use any of the features that we've kind of discussed previously, that's all there in that single repository and good to go. But I'd kind of, if you're new to STM32 and microcontrollers and stuff in general, I'd recommend using the Cube IDE because it's works really well for the these particular devices. So it's kind of similar to using Arduinos, except a decent bit more powerful and a lot more features. Do quite a bit more stuff with them, and some of the other ones that you can get do come with things like touch screens and things like that as well as being able to use SD cards and all that sort of stuff. And speaking of FPGAs, we do also have some FPGA videos that will be coming out soon as well. So talking about how to do some of that sort of stuff. So a lot of different things that I want to try and cover, but just a matter of getting the time to actually get the streams and videos done and get them put out. And yes, FPGAs can hurt your brain, especially once you start to get into them. Once you start to get a feel for them though, they can be quite fun to work with. That's why I'm doing streams rather than actually recording the videos and editing them and all of that sort of stuff, because if I just do them as live streams, I don't have to edit them. It does mean that there's probably some of the more boring stuff, like what I'm doing now, where you've got to go out and go around and sort of get everything formatted and things like that. But It does mean that I can actually get more content out for people to make use of in a shorter period of time, which I have a bit more fun with. I'd rather be spending my time playing with code than actually sitting there editing video. Used to enjoy it a bit more back in the day when I had a previous YouTube channel about 11 years ago, but yeah, these days it's not really something I want to be doing. Unless I can pay someone else to do it, which I'd rather not be doing at the moment because I'd rather be spending the money on microcontrollers. All right, so let's pop some code in here. So first up, for actually getting this thing initialized. So making use of the timer manager that we created in our timer manager video a few streams ago. Letting it know which timer we actually want access to. Make sure I do this correctly. So first up, want to check if the specific timer that we're wanting to use actually supports rotary encoders, because not all of them do. I think 5 out of the 8 timers in the device that we're using provide support for rotary encoders, so this allows us to actually go through and check this first up. And if it's not supported, then it's just going to return the not supported error. And then we're going to check whether that timer is being used by something else. So doing this a little bit more dynamically than we would be doing for, you know, if we were just hard coding a microcontroller, simply because we do want to end up having something that's a bit more like an operating system where we can sort of chop and change devices without having to recode things. So telling it that we want to register that timer is being used by this driver and that we're going to be using it for an encoder. And then we'll call our peripheral initialization method at that point. And then if that has failed, so if it hasn't been able to initialize it, then we will then deregister that timer so that something else can go through and make use of it if it needs to. Like so. And then we'll return eres, which will either be an OK or an error, depending on whether it's succeeded or not. And then just checking to see if it is initialized or not, because if it's not initialized, there's no point trying to de-initialize it. Want to do a full de-initialization, and also want to deregister the timer from the timer manager as well. Okay, so do our start, and might actually do our peripheral initialization and de-initialization methods first, because that's kind of still in the same vein. So similar to what we did previously in our, when we were testing it just in the main CPP file, we'll go through and get our GPIOs set up first. And rather than set up both pins at once, like we did with that, we're going to actually set them up separately so that if we're using 2 pins which are from different GPIOs or something like that, then we're actually getting those set up as we need them to be. So if we had one pin from GPIO-A and one from GPIO-C, we can't really initialize those together. We'd have to do them separately. So just making sure that we actually provide support for that as well. And similar to before, so just telling it what pin we're using. Going to be using mode AF push pull. No pull up or pull down. Make sure everything lines up nice and neat. And set up channel 2 as well. Might help if we actually initialize that pin. So that'll be using our channel 1 GPIO and pass it our GPIO in it. We don't need to do all of these bits for channel 2 because some of them are going to be the same as channel 1. So we're going to just need to change what pin and what the alternate is, because those are the only two things that are likely to differ in between those two pins, along with which actual GPIO we're using, which we're popping in there. So that's our GPIOs initialized. We want to enable the timer clock rather than forgetting to do that like we did before. And we can just use the timer manager to do that for us. We'll go through and initialize the timer itself. So same as before, first things is filling out a few of the details in our handle. So such as our instance, which we will grab from our timer manager as well. Our counter modes. Again, the counter mode and the prescaler aren't really being used in this instance. We'll pop them in there anyway, partly so that if we want to copy and paste this code to initializing something else related to timers, we can kind of do that and have all of our bits and pieces there as we want them. Now, we'll use the, we call it in here, so mu max val for our period. Clock division. Again, this is another one that's not actually being used. Repetition counter. Which will be FF for that one. And our auto reload preloads. And we'll enable that one. Now we'll set up our encoder init type def as well. Let's fill that one with all zeros. And this one is basically going to be the same as what we did when we tested it in main before. So let's make our life a little bit easier, and we're just going to copy that one Just going to do a find and replace on that one to fix that up with how I've named it there. Losing my voice. Okay, so let's get that initialized. So we want to give it our handle as well as our encoder init structure that we've just filled out. And if that one has not succeeded, then we want to do a partial deinitialization just to release the timer clock. So to disable that again and release the two GPIO pins that we've set up so that they can be, so that things fail gracefully, effectively. And then if we get to this point, then all of that is set up the way we want it. So we want to make sure that we set the states so that we know sort of what's going on with the driver at that point. So it'll be inactive, but it'll be initialized. So set our init state to initialized, like so. And stream still behaving, that's good. All right, so if we get to this point, everything is all good, so we can just return OK there. So that's all our initialization stuff done. Let's get our deinitialization done. So if we're doing a full deinitialization, then we want to deinitialize the actual encoder. Pass it the handle for that one. Otherwise, we basically just want to disable our clock and deinitialize our GPIOs. Again, using our timer manager to disable the clock for that one. Which GPIO using there, so that'll be channel 1, and which pin, and same for channel 2. And set our states so that we know it's neither active nor initialized. All right. So that's those ones done. So let's do our start and our stop methods next. Actually, we might do our clear data method first up, just because we're going to be using that in start anyway. So making sure that we set our value old to 0 and value new to 0, as well as our difference and acceleration both to 0. And we'll also go through and set our timer register or timer counter register to 0 for that one as well. All right. Most of the way there on this one now. So in order to actually start the encoder mode on that one, we're going to check to make sure that it is actually initialized and that it's not currently active. Go through and use that clear data method to make sure that the data is all clean and ready to go. and tell it to start that one, and then we'll set our state to active so that we know that that one is now running. And similar thing when we go to stop it, so only going to be stopping it if it's initialized and if it is actually active. Stop that one. Pass it the handle, and that's going to be for all channels. Also do a clear data. Actually, no, we don't need to because we're going to do that in start anyway, but we do need to make note that it's no longer active. And our update methods, as I mentioned earlier, is basically the one that is going to check what the current timer value is, calculate the difference in between the previous timer value and the current timer value, and then divide that by 4 in order to determine how many clicks of the rotary encoder we've actually turned clockwise or anti-clockwise. So again, we're only going to be doing this stuff if we are currently active. Put our previous new value into our old value, and then update our new value with whatever's currently in the timer counter register. Now, the particular approach that I normally use to be able to deal with whether or not the value is wrapped around in either direction is something like this. This seems to work quite well. Maybe a more efficient way to do it, but this has been used in a few different projects now that I've worked on, and seems to work pretty good. So basically, using this val comp to determine whether or not the new value is less than the old value. So if it is, then I'm going to use our diff A and diff B to calculate a direct difference as well as a wrapped around difference, if that kind of makes sense. So value new, so value old minus value new, and then diff B is our wrapped around value. So in this case, mu value new plus mu max val, which is the point at which it wraps around, which we created before. So it's essentially the period value that we're using for the timer as well. And then in our else, it's basically going to be, excuse me, basically going to be backwards. So this will be value new minus u value old. And diff B will be mu value old plus mu max val minus mu value new. And it'll do either of these based on which one is a higher value, so whether new or old is the higher value of the two. And then once we've done that, then we can then figure out whether either diff A or diff B is the larger value, because we essentially want the smaller one. Is if it's wrapped around, then if we compare just the difference in between those two values, and we have one that's say 1 and one that's 1,000, then we're going to have a difference of 1,000 or 999. whereas the wrapped around value is going to be much less, and that's going to be the correct one. So it's going to be pretty rare that you're actually turning the rotary encoder 1,000 clicks in a particular update period. So I typically be calling the update method somewhere around 2 to 10 times a second. It'd be a bit hard to actually be turning the rotary encoder that quickly. And then our I value will be that one there. So our I value, that's basically going to store the changes in the value in between each time we actually call the get value method. So whenever we call get value, it's going to calculate how many clicks have been made and then sort of reset that. But because we're actually going to get the timer counter changing by steps of 4 typically with each click of the encoder, it's also got to account for that. But we'll sort of see that a bit more in a moment when we do the get value. And then we'll calculate our acceleration value as well, which will be our difference multiplied by 1,000 divided by how many milliseconds have passed. So that way we can keep track of how fast the rotary encoder is actually being turned. So for getting our state, that's just determining whether or not the rotary encoder is currently active, which we're storing in ME state. So we can just retrieve that. For our get value though, as I was saying before, firstly you want to check if it's actually initialized, and if it's not, we're just going to return 0. If it is initialized, then we'll calculate what our value is that we're going to send out, which we'll get from, type that correctly, so that'll be I value divided by 4, because it's 4 ticks of the counter for each click of the rotary encoder. And then we're just going to do a mod by 4 on our I value, so that sometimes when you turn the rotary encoder, it may only move, say, 3 steps of the timer counter. Sometimes it's not always consistent. So by doing it this way, it actually filters that out, and then the values that we're actually getting, which we'll use in our user interface or whatever we're using the encoder to control, we will get consistent values. And over the projects that I've used this particular approach with, it's always worked really well. So we'll stick with doing it that way. And then depending on whether we've got our driver in linear or exponential mode, will determine how we do our output value. So if we're in exponential mode, so in that case, E mode will be true, then we're going to go through and basically cube our output value. And the benefit of cubing it rather than just squaring it is it retains whether it's positive or negative. Whereas if we were just squaring it, we're always going to get a positive regardless of which way we're turning the rotary encoder, which kind of doesn't work. But if E mode is false, so if we're in linear mode, then we'll just return I out val as it is. And then last 3 methods on the driver, nice simple ones, all one-liners. So for this one, we just want to retrieve our acceleration value. So if it's initialized, then we'll retrieve that from mu excel, which we calculated in the update method. Otherwise, we're just going to return 0. And then for setting our mode, it's just a matter of setting ME mode to what we're passing into that function. And then for this one, we're just returning ME mode. And that is all of those done. Fix up that spelling mistake in the comment there. And let's see if that builds. Error is there somewhere. Okay, we've got a couple. That one's pretty obvious. Ah, that should be UNT16T. What's this one? Ah, that's the same error. But just those guys. Oh no, there's some errors in here as well. What do we got? That should just be pin. And that should be E state. Rather, should be ME state actually. So we're checking whether or not we're active and stopping if it is. That should sort all of those out. There's still 2 errors. One more left in here. That's right. They always do D in it with a capital I in the HAL code. Excellent. All right. So let's go through and actually get this tested. So first things first, let's pop this in after where we were playing around with the raw code before we started on the driver. So we're going to want firstly to go up the top of our main and include our Q8E encoder.hpp, and also do a global declaration of our driver class for that one. Let's call it encoder test. That's all we need to do for that one. And we'll need a Q8E encoder init struct to tell it how we want that initialized. And using GPIO and pin 4, channel 1 pin, GPIO pin 4, and set our alternate function for that pin, which will be using GPIO AF2 timer 3. It will be similar for our channel 2 pin. Except that will be pin 5 on GPIO. And then we just need to let it know which timer we're using and whether we're using linear or exponential mode for that one. So timer will be timer 3. That will be Q8E encoder mode. We'll just go with linear for the moment. And then we can get that initialized. So encoder test equals new Q8E encoder, and just pass in encoder init there. Just double check. Okay, we are passing that in by reference, which is good. So it's not copying the init structure. Save ourselves some clock cycles there. And then we'll tell it to go ahead and initialize it. Should be encoder test. Might help if we put the right name in there. And if it fails, we will turn the user LED on and print out of the UART to the laptop to let it know that that has failed. And we'll chuck that in a infinite loop in that case as well. However, if it's succeeded, we will pop a message out to show that. Actually, we'll also, if it's succeeded, we'll go ahead and start the encoder at that point, like so, and then in a message that we send out, we'll just go initialized and started. All right, and then similar to what we did with when we were just roughly testing the encoder stuff before, we're just going to every 1 second just update or output a value to serial to show what changes have happened to the encoder, so how far we've turned it in either direction. So for that one, going to be fairly similar, but choose a uint16 there. We'll also call that uval, because that way we don't have to modify these few lines of code here. That bit. And then let's go encoder test and get value. And unless I've forgotten something, that should work fine. Compile's fine. Let's pop it on the device. Okay, it's updating fine. It says it's initialized fine. However, we're not getting any change to the value when we rotate that one. So something has been missed. Where are we? Okay, definitely using the right pin, so B4 and B5. Using the right timer. We are actually starting that one, so that should be fine. Of course, we need to call our update methods. And pass it encoder tick so that it knows how much time has passed since our previous update. So without that, we're not going to get any values. So that should hopefully work a little bit better. So we'll just compile that and pop that on the device. And something not working correctly there. Everything plugged in right? There's some strange values out there, which means that seems to me that's not hardware, that's code. So check our update methods, make sure that we haven't messed anything up in there. That's all correct. Wait. Okay. Didn't think that looked right. We need to actually be returning a particular value depending on whether diff A is less than diff B there. So that would kind of explain that. A little bit of an oversight. I don't think it would be one of my streams without at least a couple of weird bugs due to me not paying attention. That's half the fun of it. My excuse is it shows people how to actually find weird little bugs like that, and I'll stick with that as an excuse. I think that works fine. Okay, downloaded. Let's jump back over to this one. That looks better. We're getting positive values as we rotate clockwise. However, anti-clockwise does not work correctly. Should be getting negative values in that case. And the fact that we're getting this is a signed versus unsigned issue straight away, which will be because that should actually be signed. Would be helpful. And we'll just check that our get value method is actually returning. Yeah, it is actually returning a signed value. So because we were returning a signed value and popping it into a uint16 instead of an int16, that's why we're getting that. So it was getting the right value, but it was formatted as an unsigned value. And pop that back on there. And let's see what we get now. Okay, getting negative values when we turn any clockwise. All right, working like a charm. So if we turn it one tick, we get showing up as 1. And we go just 1 tick in any clockwise. That's all working correctly as well. The other thing I just want to test is our exponential mode. So we know that it's working in linear. Pop it in exponential. Actually, I think that should just be EXP, right? Yeah, that's correct. All right. Try that one out. We turn it fast, we get really big changes in value, which is what we want. And same in the opposite direction, but we can still just do it just 1 tick in either direction and it still picks up that. So In exponential mode, we get what we need, which is the ability to have really fine control, but also to move through a bunch of values really quickly. So if we've got, say, a big list of options or something we're scrolling through in a user interface, we can do that without having to keep turning the rotary encoder a bunch of times, which is typically the way you'll find it done with rotary encoders in most properly developed consumer electronics. They tend to use more of a exponential mode rather than just doing it linearly, so that the acceleration of the rotary encoder is actually taken into account. So pretty happy with that. That all works as it's supposed to. So as I mentioned a couple of times, this code, much like the code from our previous videos, will be going up onto GitHub, typically within about 5 to 10 minutes after the stream, and I'll be popping a link to that one both in the description for Twitch and also on YouTube. If there's any questions or anything like that, feel free to pop a comment, or jump onto our subreddit r/ones and zeros, or send me an email if you'd prefer to do it that way, which is onesandzeros.contact@gmail.com. Always happy to help out, answer questions. If you want to know how to use specific bits and pieces of the code that we've done over the previous videos and you can't find it in one of the specific videos, definitely feel free to pop me a question. Or if you come across any bugs or anything like that in any of the code as well, definitely let me know so that I can get them sorted out. And if you'd like to help support the channel, definitely love it if you follow us on Twitch or like and subscribe the videos on YouTube. Thank you again to all of the people that have become followers or subscribers recently. There has been a few that I've noticed, which I do think is really cool. There's been, I think, over 400 views on YouTube in just over a month across all of the videos, which I think is really cool for doing STM32 code. It's not like viral videos or anything like that. Also, there is also a Patreon, so if you want to jump on there to help support us too. And also, there will also be a bit of a giveaway coming up when we hit 100 subscribers on YouTube. So there is the possibility of actually scoring yourself some cool microcontroller stuff at that point. So keep an eye out for more information on that over coming videos as well. So thank you so much for watching. Hope you enjoyed that one, and hope to see you next time.